If you haven't heard of chaos theory before, then you probably live under a rock. See, chaos theory is one of the most popularized branches of mathematics out there. It's seen everywhere. It's mentioned in Jurassic Park. It's the focal point of some philosophies that discuss free will, fate, and destiny, though that's a bit above my pay grade as a math content creator, so we won't be discussing that. Anyway, so what is chaos theory about? Well, it's about chaos. Chaos theory is about chaos, which is synonymous with the butterfly effect. So, no, we're not studying insects. The butterfly effect is the idea that small differences in the starting point can lead to drastically different outcomes later on. So mathematically speaking, this definition is okay, albeit a little bit informal. You won't be presenting this at math conferences or anything like that. So anyways, in this video, I'll be covering the formal mathematical definition of chaos. And I'll also be clearing some common misunderstandings about what chaos actually is. Now for the more boring part of the video. So before we define chaos, we need to define 5 things. One of them is a dynamical system, which is the most fundamental object in this entire field. We need to define what a deterministic dynamical system is. Then there's 3 properties that define chaos. One of them is sensitivity to initial conditions, topological transitivity, and the density of periodic orbits. And so I'm going to be defining all those 5 mathematical things later in this video. So what is a dynamical system? Well, a dynamical system is basically just a set of equations that describe how something changes, and that something is pretty much always denoted with a variable. Take this example. So suppose you have the real number line, and you have a grasshopper where every single second it jumps by 1 unit to the right. So you could say that every single time that it's on the number line, it is 1 unit forward compared to the last step. And so you could describe this sequence of steps with an equation stating that the nth term in the sequence is, or any given term in the sequence, is always 1 greater than the previous step. And you'd have to define the initial condition or the starting point. And so this describes what's happening in the system quite nicely. Okay, and this is an example of a discrete time dynamical system, by the way, because all the time steps are done discretely in steps of 1. Now, if you've taken calculus, then this example's for you. If you haven't, don't worry about what I'm about to say. You could skip the next 30 seconds. So the continuous time dynamical system is a differential equation, and you might recognize this as exponential growth formula. And by definition, the derivative describes how a system changes. So dx dt equals 5x is pretty much just a dynamical system, but over the continuum. So this can describe change across the whole real line, for example. Okay, great. So now that we covered what a dynamical system is, we can talk about what a deterministic dynamical system is, which, by the way, both of these examples are. What is a deterministic dynamical system? Well, it's a system where there is 0 randomness, which means that if you pick the same initial condition, run it 100 times, you'll get the same outcome every single time. And so, say you take the grasshopper example from last time. Say he's hopping 1 meter every second. You let it elapse for 5 seconds. Well, if you run the experiment 1,000 times, Jiminy Cricket is going to end up at the 5-meter mark every single time. And in fact, another consequence of a system being deterministic is that if you know the equations and you know the initial condition, then you can actually predict where the system will be at any given point in time, no matter how far in the future. So yeah, basically in this system, everyone's fate is decided. It's predetermined. I'll now be covering the definition of initial condition sensitivity. And I will not be presenting this formal definition. I'm going to be presenting the general idea. So suppose that you have a point X, and then you take a really small ball of radius R. You could say R is like 10 to the negative 100,000. doesn't matter how small it is. It can be arbitrarily small. And then you take a point y inside the ball. So that means that the distance between x and y must be even smaller than r since y is inside the radius. So, oh, and by the way, y cannot be equal to x. The idea is that if you iterate the system forward enough times, by the way, f is the function that will take a point and then lead it to its next step in the dynamical system sequence. If you iterate it forward enough times, eventually you'll get a point where x and y has a distance that exceeds some value r, big R. And this big value r exists no matter how small you make this radius r. So, okay, let's first of all make sense of what this all means. It means that no matter how small of a difference that you have between starting points, it will always diverge to a pretty big degree. Even if you make this 10 to the negative 100,000, eventually x and y are going to be separated by this big R. It could be a big value, could be small, but at least it'll be bigger than whatever we have here. So yeah, this is what they mean by initial condition sensitivity. The difference could be the tiniest thing in the world, but it won't matter because they will diverge eventually. Okay, so this is the essence of what chaos theory is about, initial condition sensitivity. It's not the only definition, or sorry, it's not the only requirement for a system to be chaotic, but it is the most fundamental one. Here's one common misconception about chaos. So people will say that the world is chaotic, and because of the butterfly effect, there's a level of randomness in everything, and because of this randomness, things are hard to predict. So actually, I will agree about two things. One is that yes, the world is chaotic, and yes, things are very hard to predict in this world. But it's not necessarily because of the randomness, because chaos is actually deterministic by nature. And so what does deterministic mean? Well, as we mentioned before, it's like if you have the same initial conditions, you'll reliably get the same outcome every single time. As long as you know the equations and the initial conditions, you can predict how the chaotic dynamical system will behave no matter how far in the future. Well, so why are things still hard to predict in the world? Well, for one, we don't have all the equations, but two, it's because things are really hard to measure in the real world. Take this ruler, for example. I could try to measure the length of my finger. It looks like it's 3 inches, but you can never be infinitely precise about these measuring things. And because things are hard to measure in the real world, this actually is a real pain in stuff like forecasting and stuff. Because if the real world is chaotic, you can't actually predict your initial condition properly, then these small differences in what you think the initial condition is and what it actually is. In a chaotic dynamical system, small differences in initial condition lead to noticeable effects later on. And so because of that discrepancy, you can't predict anything reliably. Now, maybe that's a bit of an exaggeration. We have pretty advanced tools, but we can never be 100% sure because we can never predict something infinitely precisely. Okay, anyways, back to the boring topological transitivity stuff. The second condition for chaos is topological transitivity. And actually, this definition is quite short, so I won't leave much content out. So suppose that you have two sets of points, u and v. You can think of them as blobs in space. And suppose the equations governing the motion of these blobs in space is actually a chaotic dynamical system. Then for it to have topological transitivity, it's a requirement that if you say you fix v, freeze it in time, but you allow it to go forward in time. Now, eventually u will have to intersect v. That's essentially all that topological transitivity means. You can choose u and v to be whatever you want. you will eventually have visited V at least once. And you can kind of, an analogy would be that you could say that every single blob or set in this, in the entire space is kind of like an avid traveler. And by the end of its journey, it'll have visited every single place in the entire universe. I think that analogy was good. Okay, anyways, moving on to the third condition. The third and final condition for chaos is the density of periodic orbits in space. Now, what the hell does that mean? Well, first I'll introduce what a periodic orbit is. So you know how the Earth orbits around the sun, right? I think you should know that. It takes about a year, and then at the end of that year, Earth ends up at the same place as it started. Well, so that is actually a periodic orbit, where you start off at a point called a periodic point, you iterate it forward some pre-specified time, and once you do that, you end up at the exact same place that you started. So, yeah, that's what a periodic orbit is. And the density of periodic orbits, what that means is that if you take some random point in space X, doesn't have to be a periodic orbit, just some random Joe Schmo point. You take a radius r, doesn't matter how small it is, could be like 10 to the negative 1 millionth power, could be that tiny, doesn't matter. You'll always find that there is a periodic point P inside that really small radius. So what does that mean? Well, it means that there's a lot of freaking periodic points in the system. I don't know if there's a deeper meaning to that, but anyways, yeah, that's the third mathematical condition. It means that there's a lot of periodic orbits present in a chaotic system. So again, just to review, a chaotic dynamical system, or the butterfly effect, consists of 4 key things. The fact that it's deterministic, its sensitivity to initial conditions, topological transitivity, and the density of periodic orbits.